I think we're ready to discuss the applications of residues now. So I want to take you back to the good old days back in Calc 2. You were probably in 217 when you saw this. And you talked about indefinite integrals. And so remember, the integral from 0 to infinity of f of x dx is defined as a limit. It's the limit. You probably would have used a t, I'm guessing. The limit is t goes to infinity of the integral from 0 to t of f of x dx. Remember doing that? And in a similar vein, you could define the integral from minus infinity to infinity of f of x dx. You probably did define this if you guys looked at this as the limit. I'll need two different variables. Let's say t1 goes to infinity. So of the integral, let's do the minus part first, of minus t1 to 0 of f of x dx plus the limit as t2 goes to infinity of the integral from 0 to t2 f of x dx. And so a couple of things. This is important that we pay attention to when this integral actually converges. So let's switch colors here so we can see it maybe. This integral converges when both of these pieces converge. They both need to converge to a finite number. So that's when this one converges. All right? So that's the background that I need from what you would have seen in Calculus 2. Now I'm going to give you a definition. So the Cauchy principal value of this improper integral is the limit, and first off we're going to write this PV minus infinity to infinity of f of x dx. That stands for principal value, and this is the limit. I'll probably switch to just an r here for reasons that you'll see later on. R goes to infinity of the integral from minus r to r of f of x dx. Okay, so of course this is all provided that this limit exists. So the Cauchy principal value exists precisely when this limit exists. And so the question is, how is this related to the original integral? So I'm going to refer to this improper integral as star. So when I write star down, I'm referring to this guy. So let's make a couple of comments. So if star converges, star being, you know what, we can actually pull this one down, and that way we can see it down here. So if star converges in the usual sense as the sum of two limits, both limits exist, so both limits associated to this integral exist, then actually star converges to its Cauchy principal value. So let me say it again. Let's scroll back up. If this integral converges, then this guy converges, and this guy converges, and this integral is the sum of this one plus this one. Okay? When that happens, when this converges, it is equal to its Cauchy principal value. In other words, when this converges, then this and this are the same. And I know we'd all really like to say, oh, they're always going to be the same. Not true. It may be that the Cauchy principal value exists, converges, but the whole thing doesn't. That's what's sadly not true. If the improper integral converges, then it converges to the Cauchy principal value. But if it doesn't converge, it's still possible that the Cauchy principal value does converge, giving you a false answer. So I've captured that here in part 2, remark 2. So it's not true that star converges whenever the Cauchy principal value exists. And just to make sure that you believe that, I thought we should do an example. So let's just look at the principal value of the integral from minus infinity to infinity of x dx. So this is the limit as r goes to infinity of the integral from minus r to r of x dx. So far, so good, no problems. This is going to be the limit as r goes to infinity of what? When we integrate x, we get x squared over 2, and we're going to evaluate this from minus r to r. And now when I plug in r, I get r squared over 2 minus r all squared over 2. And you just get r squared over 2 minus r squared over 2. So this is the limit as r goes to infinity of 0, which we all know is 0. So the Cauchy principal value of this integral is just 0. However, if you look at the improper integral, minus infinity to infinity of x dx, the true definition is the limit as r1 goes to infinity of the integral from 0 to r1 of x dx plus the limit as r2 goes to infinity of the integral from minus r2 to 0 of x dx. This all feels very similar, but it's not the same. Limit as r1 goes to infinity of what? X squared over 2 evaluated from 0 to r1 plus the limit as r2 goes to infinity of x squared over 2 evaluated from minus r2 to 0. And now let's see what happens. So here I'm going to get the limit as r1 goes to infinity of r1 squared over 2. When I plug in 0 over here, when I plug in 0, I get 0, subtract, plug in minus r squared. So you're going to get a negative from the subtracting, not from the minus r2. Negative r2 goes to infinity of r2 squared over 2. And now you see what's happening. Okay, the full improper limit converges if and only if this part converges and this part converges. But this part is blowing up to infinity. And this part is blowing up to minus infinity. And it's so tempting to say, oh, well, but they're going to cancel and go to 0. That's not the point. The point is that neither piece is converging, therefore the whole thing is not converging. And the warning is the Cauchy principal value actually did exist and it went to 0. It did exactly what you would sort of expect when you look at these, right? If I could combine them somehow, but I can't. These are different limits and I'm thinking about them separately. And since neither one converges, the full thing does not converge. So that's just a warning there to be careful. And in the next video, we'll talk about a special case when you know that things work out nicely.